I think it does a good job, but depending on who you ask, it may do an okay job of this. So it turns out actually that protons and neutrons, I've been saying over and over that these make all the elements, that this is what we are made of, you should care about this. But actually, it turns out that protons and neutrons further break down into even more fundamental particles called quarks. Okay, so these quarks are also things that we'll talk about. They also belong to a family of particles. So quarks is the other family of particle. Then there's another family of particle that I alluded to, which is the leptons, and electron is a part of the lepton family. Okay, do you have your PhD? Yes, it's in physics. So leptons is the is the family of particles that electrons belong to. Electrons don't actually belong to the same family of particles as the neutrons and the protons belong to. Neutrons and protons are made up of things called quarks, and these are its own family of particles. And then there's bosons, which are the force carrier particles. Photons are a type of force carrier. Gluons are a type of force carrier. W and Z bosons are a type of force carrier. So understanding these forces, once again, it's like the fundamental forces are the same. It's like the what I just said is the same as understanding the fundamental forces. So we want to understand the fundamental forces because it's all like that's all the forces of nature. We really would want to understand them. If there's something else that's going on, we want to understand that too. If it's unknown to us, of course, we would be like, oh my gosh, well, particle physics is incomplete. We have to add to it. But pretty much of all the things that we understand, know, and love, the four fundamental forces is very important. And associated with those four fundamental forces are these types of particles and force carrier particles that are also important and summarized by particle physics. In other words, it is called standard model of particle physics. Okay, so this stuff that I just said, the leptons, quarks, and bosons, or the fundamental forces of particle of nature, is actually part of the standard model. And so you might hear, what does the standard model say? Standard model of particle physics is basically this. And standard model of particle physics, unfortunately, does not explain gravitation. So it includes it in the table, if you will, but it doesn't actually have an explanation or a discovery for the particle nature of gravitation or the gravitation particle or anything like that, right? So just letting you know that it's really mostly the non-gravitational forces that are explained by particle physics. Okay, so listen to the rest of this to kind of get this hit this home, if you will. So I have already discussed, or these four fundamental interactions are the ways in which the various elementary particles from which all matter is made interact with each other. So once again, that's the sentence I was explaining, where everything we're made of, everything we know and love, periodic table, everything is basically interacting with each other with these fundamental forces. I've already discussed two of this, electromagnetism and gravity. The other two concern the interactions between the constituents of the nuclei of atoms, the weak nuclear force and the strong nuclear force. So by the way, the strong and weak nuclear forces are the two fundamental forces that we discovered later on, because of course, most people at the ordinary scales will not interact at the nuclear scales where those forces become important. See, as human beings and as classical scales, as far as classical scales go, and by classical, I mean Newtonian mechanics, classical physics, electromagnetism, gravitation, general relativity. These are classical physics. They affect scales or length scales that make sense to us. What are these length scales? Like people scales, tree scales, earth scale, moon scale, Grand Canyon scale. These scales, at these scales, classical physics is more of a thing. At those scales, pretty much the forces that we cared about or we dealt with were gravitation and electromagnetism. But then came quantum mechanics. So do you see how it's all connected? Why do we care about the strong nuclear force and weak nuclear force? Why do we now have four fundamental forces? Why do we care about unifying the four fundamental forces? It's because we've also discovered more things. We have discovered the strong and weak nuclear forces, and we have to now explain them too. But why did we discover them? It's because of quantum mechanics. We started to learn and study the physics of the very small quantum scales, tiny scales, subatomic scales, the hydrogen atom, right? Because we were interested in those smaller scales, which is not classical, we had to develop non-classical physics or quantum physics and do a whole, like basically develop a whole new field, which is quantum physics or quantum mechanics. And this is where the strong nuclear force and the weak nuclear force come into play. Before that, we didn't even know about them. They weren't even a thing that we really bothered with, okay? So the other two concern the interactions between the constituents of the nuclei of atoms. Once again, the strong nuclear force and the weak nuclear force. The four forces vary in strength. That's the other thing, is that I've been saying how we want a way, a theory of everything, a way to unify these four forces. But guess what? The forces are quite different from each other as we experience them now. Gravitation is the weakest, and it's an always attractive force. So I keep saying how the non-gravitational forces still have some hope of unification, and they have been unified to some extent. You need very extreme environments and temperatures and scales, but they can be unified. But gravitation is kind of quite uniquely different. It's the weakest one as far as strength goes, and it's an always attractive force. There's no repulsion in gravitation, as far as we know anyways, right? Electromagnetism is, for example, sometimes attractive and sometimes repulsive forces. Two charges, if they're oppositely charged, they will attract. If they're similarly or like charged, if they have the same charge, then they will repel each other. So electromagnetic force is sometimes attractive and sometimes repulsive, and has a strength quite different than that of gravitation, and is more strong. Actually, the strength of electromagnetic force is stronger. So the four forces vary in strength. Gravity is the weakest, and the strong nuclear force is the strongest. The strong nuclear force is very strong. It impacts, of course, subatomic, the subnuclear particles, the quarks that are within the nucleus. The protons and neutrons, they interact through the strong nuclear force. So that one's the strongest, and we didn't even discover it until much later. But anyways, and also in the kinds of elementary particles that take part in the interactions they control. The electromagnetic force holds electrons in orbit around atomic nuclei, and is thus responsible for holding together all material with which we are familiar. So, you know, strong nuclear force, of course, affects. Oh, my earphone just changed the mode, and I could hear my voice different now. The strong nuclear force, of course, affects what's within the nucleus, but the electromagnetic force, which is less strong than the strong nuclear force, but still a very important force because it keeps electrons in orbit around the nucleus within an atom. So if atoms would not be a thing, if not for the electromagnetic force, right? The electron is opposite charge than the nucleus. See, protons have positive charge. They're made up of further divisible fundamental particles called quarks, and altogether, protons have a positive charge. Because this positive charge is attractive to negative charge of the electron, so then we have electrons and protons kind of staying together, kind of sort of staying together in the atoms. And we have atoms and we have neutral atoms, right? Otherwise, we would just have nuclei. And, you know, depending on the temperature and depending on your energy regime, at higher temperatures and higher energy regimes, like back to when Big Bang was happening, there were no neutral atoms. So if you're just wondering about that, then just forget it. There were no neutral atoms back when Big Bang nucleosynthesis was happening, because things were too hot, too dense, too much energy at that time for electromagnetic force to do anything, and we did not have neutral atoms. But at the energy regime where electromagnetic force can operate, there electrons and nuclei are oppositely charged, so they attract each other. We get neutral atoms. Everything is nice and dandy. This is not always the case, of course. Things can get charged and lose an electron. That's actually how all of chemistry works, is the interchange and electrons going here and there and whatnot. But or say electricity flowing through a metal is because a metal actually has a bunch of sort of free electrons where the electrons are not so tightly bound to their nuclei. They're sort of not so they're not so tightly married to their nuclei. They're kind of free, and so they flow more freely, and we get electric current, right? But all of this stuff, whether how much electromagnetic force you have or how much you don't have, whether electromagnetic force is a thing or not, will give us neutral atoms or not. So of course, again, very important, right? So very important to understand all this. However, it was realized early in the 20th century that in order to apply Maxwell's theory in detail to atoms, ideas from quantum physics and relativity would have to be incorporated. Because again, it's the theory of the very small, or the physics of the very small. When you go to subatomic levels, scales, length scales, where you're looking inside of an atom or thinking in terms of even the electron, even to actually write down the equation of motion or equation of motion. How is the position of an electron, for example, changing with time? This is actually something that we can think about, right? Because in physics, we love to write down equations for things, and we love to write down equations of motion, for example. We have laws of motion from Newton's. We have laws of gravitation, which is also sort of motion, right? Or the laws of motion of the planets, how we figured out all the things with the Earth going around the sun, all the other planets, what they do. When is Mercury retrograde? When is Jupiter here or Jupiter there or Saturn? Or all, those are all basically coming from equations of motion of the planets. So now think about it, but for the atom and for the electron and nuclei, at those other scales, actually, to get the equation of motion, we would need to incorporate quantum mechanics. We cannot have a classical equation for that. So quantum mechanics gives us, for example, the equation of motion of electron, and it turns out that it's actually kind of a wave equation. We get sort of a wave equation for this thing. We don't get a standard, just boring kind of, oh, the electron is here at this time. No, it's kind of a wave. And on top of that, it turns out that the wave equation is actually kind of giving us the probability of finding the electron at a certain time, not the exactly where the electron will be. So in quantum mechanics, all we get is these wave equations, and they actually give us probabilities of finding the electron. So all of that is to say that you may be interested in understanding electromagnetic force because of all these things, because it's so important. It gives us neutral atoms and makes electricity flow and all of that good stuff. But you cannot ignore quantum mechanics when it comes to these small things. When you try to understand what's happening at the scale of an electron or an atom, you have to remember good old quantum mechanics, or maybe good new quantum mechanics, because at that point, quantum mechanics is not that old in the 20th century. So might have been a little uncomfy for these people, and they had to kind of do some work about it, right? So anyway, however, it was realized early in the 20th century, so in the early 1900s, that in order to apply Maxwell's theory in detail to atoms, ideas from quantum physics would have to be incorporated, and also probably relativity, right? Actually, Dirac turned some of those quantum mechanics equations to include relativity, and they were then relativistic quantum mechanics equations, okay? So it was not until the work of Richard Feynman and others, so now we're getting closer to the title of this life, quantum electrodynamics. All of this was to motivate why we even need such a thing, but hopefully you get the context. So it was not until the work of Richard Feynman, you might have heard of this guy, Feynman. He has contributed largely to particle physics and what we're about to talk about here. So Feynman and others, building on the work of Dirac, I just mentioned Dirac. Dirac is the guy, by the way, who took the quantum mechanics equations and turned them relativistic, that a full quantum theory of the electromagnetic force called quantum electrodynamics was developed. So basically, all of this is to say that we needed a quantum friendly electromagnetic force or electromagnetic force theory or electromagnetic theory, because of basically electromagnetism classically, even though is explained by James Maxwell and others, Michael Faraday, etc., with the electromagnetism equations. We actually have a set of equations, Maxwell's equations, they're called. So classically, we learn a lot and can use these equations, and they pretty much tell us everything about everything. But if you were really, truly interested in understanding things at a subatomic length scale level, then the classical equations are not enough, and you might want to incorporate quantum mechanics into these things. And that is called quantum electrodynamics. Okay, so it's not so scary of a thing. This live is not that scary or not that bad. It's just quantum mechanics in electromagnetism. Okay, so no need to worry. Let me share the live one more time, actually. I'll take a little breather, 1 or 2 minutes, and then I'll get back to it. So quantum electrodynamics, if you're looking at this live title and being like, what is that? And do I want this? It's very important to understand, why it's even a thing, the context of it. And it's not that bad. It's just electromagnetism, but also incorporating quantum. Okay? And it makes sense because electromagnetism, electric currents, what is that? Electrons. Electron is what? Small. So small stuff needs what? Quantum mechanics, because quantum mechanics is the physics of writing things down for small stuff. Specifically, it is the physics or the mechanics. Sometimes it's called quantum mechanics because it's the laws of motion, if you will, equations of motion, equations of states, or wave equation. These are sort of the things that we say sometimes. But all we want to know is, where is this little thing at? Say, what is this thing's position as a function of time? We want to write that down, for God's sake. So what do we do? How do we do it? There's this wave equation way of doing it for quantum mechanics, in quantum mechanics, for tiny small particles that follow quantum mechanics, such as what would be needed in the case of an electron. And that wave equation is generally giving you a probability answer, which is the way of things in quantum mechanics. It's just the nature of quantum mechanics. And that is what needs to be incorporated into electromagnetism as well. So that's what quantum electrodynamics is. And we will read more in just a second. Let me share this one more time. Thank you for being in the live, by the way, everybody. Really appreciate seeing everyone here. Okay, so quantum electrodynamics, okay? Electromagnetism with some quantum included, because why not? Because quantum is important at those scales. Okay, so let's see. In this theory, usually abbreviated to QED. So if you've ever heard of, or if you've ever seen QED, what is that? Like, what does that mean? It's just quantum electrodynamics, okay? And what is QED? It's just electromagnetism with some quantum mechanics included. So in QED, electromagnetic radiation in the form of photons is responsible for carrying the electromagnetic interaction between particles of different charges. So obviously, right, I was giving you the example of electrons because electrons are so important, obviously, in electromagnetic force, or sorry, in electromagnetism as a topic in general, because electrons carry electricity, and we've got equations to describe all that with electromagnetism, equations coming from Maxwell and others. And that's the classical theory. But an electron is a quantum particle, so of course we need quantum mechanics to describe it. But another thing that also has a quantum nature is, of course, light. Electromagnetism is electromagnetic waves. Electromagnetic wave is basically light. The classical nature of light is electromagnetic waves. The quantum nature of light is photons. So we already knew that light has dual wave and particle nature. So all you're doing now is just saying, hey, electromagnetic interaction, the force carrier there is a photon, instead of calling it light, and instead of acknowledging only its classical nature, which is light, and wave nature of light. The classical nature of light is wave nature of light. When we regard it as a wave, it's generally at larger scales where it behaves more like a wave. If you are interested in smaller scales where it might behave more as a particle, then we would regard it as a particle. Both natures need to be acknowledged depending on the context. So if you're at larger scales, say radio waves have larger wavelengths. So those, at that point, you can call the thing an electromagnetic wave. If you're at smaller scales, such as gamma rays have smaller wavelengths, at that point, you might call that light a photon or a particle light, a particle of light, instead of instead of the wave nature of light. So once again, depending on context, light too has dual nature. It's called the old quantum mechanics, which Einstein also contributed to, even though later on he became a little bit against quantum mechanics. Okay, so before discussing interactions any further, it is worth mentioning some of the properties of the elementary particles between which these forces act. Okay, so we kind of get what QED is. Now we're going to talk about all the different elementary particles and what is interacting with what in what way, who is interacting with who in what way, all that stuff. The basic properties are particles. The basic properties are particles called fermions. Okay, that's a weird sentence. Fermions are a type of particle. They're a basic type of particle. These are distinguished from the force carriers, the bosons, such as the photon, by their spin. So I told you about the leptons, quarks, and bosons. Another sort of way to categorize particles in particle physics is the fermions versus the bosons. Fermions are matter particles, and they have a different quantum. There is this property in quantum mechanics called spin, quantum property of matter, or any of the particles really, called spin. And this is different for the fermions versus the bosons. So we have actually covered more about what spin is and what it all means in previous lives, especially if you go, I believe it was in the lives where we covered Brief History of Time by Stephen Hawking. We talked about spin, if you're interested, and also in other places as well. But basically, to keep things simple, sometimes people categorize particles in particle physics based on this spin only, and the ones there's fermions with a certain spin, and then there's the rest of the particles or bosons, which have a different kind of spin, and we'll see how it's different. So these are distinguished from the force carriers, the bosons, such as the photon, by their spin. You'll see how it's actually spin 1/2 or a whole number of spin, which distinguishes whether the particle is a fermion or a boson. But we'll keep going. The fermions are divided into two classes, the leptons and quarks. So good thing is that he's mentioning the particle families like I was mentioning before. Once again, all the particle families are summarized by just leptons, quarks, and bosons. Depending on spin, if you want to categorize them, it's fermions and bosons. Fermions are the matter particles, which are basically leptons and quarks. Each of these classes is divided into 3 generations. So now we'll get into the generations, and I'll show you the table that summarizes these generations. Okay, so don't worry about remembering these. We will see them in just a minute. So these 3 generations are, you will see that there are 3 sort of matter generations, depending on the mass, the charge, the color in some cases, you will actually be able to say exactly which particle it is. And we will look at the table in just a second. So anyway, each of these classes is divided into 3 generations, and each generation contains 2 particles. Altogether, therefore, there are 6 leptons arranged in 3 pairs. One of each lepton pair is charged. The electron is an example, while the other carries no charge and is called a neutrino. Boson is spelled as B-O-S-O-N. Boson is a force carrier particle. In particle physics, there are the particles that make up matter, such as leptons and quarks. A lepton example is the electron. A quark example is, for example, the up quark, and quarks are what make up protons and neutrons, which make up all the elements that we know and love. And boson are the particles that carry the forces between all of these other particles. So they are, for example, photon is an example of a boson, B-O-S-O-N, okay? So we'll keep going. One of each lepton pair is charged. The electron is an example. while the other carries no charge and is called a neutrino. So this is, listen to these words. We will summarize really nicely in just a bit, because this is a lot of detail. This is not necessarily how I would present it, but we'll keep going for a bit. While the electron is stable, the other two charged leptons, called the muon and the tau, decay very rapidly and are consequently much more difficult to detect. So depending on the lepton of interest. So I said electron as an example of a lepton in the particle family, leptons, because the electron is something we know and love. We all kind of get it. It's what's involved in electric currents, obviously carries electricity. It's in the nucleus of, or sorry, it's in the atoms of things. All the atoms have nuclei, and then they have electrons, one or more, depending on which element. And that's what makes up the neutral atoms, right? If not for the electrons, all the atoms would be positively charged because of protons in the nuclei. So electron is a lepton example that most people know. So it's the most commonly understood and known lepton. But there are actually a couple other leptons that are sort of in that same family as electrons. They're called muons and taus. But these actually decay much more commonly or much faster than an electron. So that's why we don't encounter them as commonly, but they are things. And then there's also another type of leptons in the same lepton family. So think of it as a cousin of the electron. We also see a particle called neutrinos. Neutrinos also have three generations: electron neutrino, muon neutrino, and tau neutrino. And these are all within that lepton family. So once again, the lepton family is electrons, muons, taus, electron neutrino, muon neutrino, and tau neutrino, or just neutrinos if you don't want to remember the flavor names. But these are the leptons. Then there's another whole family. So this family chapter closes. Open another chapter for another family, it'll be the quarks, right? And the quarks actually are called up, down. These are what make up the protons and neutrons: charm, strange, top, and bottom. So those are the 6 types of quarks that we see. And then there's, of course, force carrier particles, which are the photons, the gluons, and the W and Z bosons. Photons are the carrier of the electromagnetic force, gluons are the carrier of strong nuclear force, and W and Z bosons are the carrier of weak nuclear force. It's a lot of detail, but this is the summary of the standard model of particle physics that I thought you'd be interested in. So the quarks are all charged, and the 3 families of them are also arranged in pairs. The first family contains the up and the down. The second pair is the strange and the charmed, like I just summarized. The third contains the bottom and the top. Free quarks are not observed, however. They are always confined into composite particles called hadrons. So a hadron's example would be the proton or the neutron, for example. These particles include the baryons, which are combinations of 3 quarks, the most familiar examples of which are the proton and the neutron. So again, the baryons, like I was mentioning, is a composite of quarks. The most familiar ones are, of course, the protons and the neutrons, and these are the ones that we know and love. And pretty much in cosmology, that's what people mean. They mean the protons and neutrons generally when they mean baryons. There are many other hadron states, but most of them are very unstable. So you might make these hadron states, which are composites of quarks, but if they're super unstable and you never meet them in real life or in nature, then it might not be something that you want to deeply study. They might be produced in accelerator experiments, like the ones we've set up, for example, at the Large Hadron Collider, et cetera, or in the Big Bang, but do not hang around for long before decaying. So unfortunately, a lot of these more exotic particles, if you will, in the particle physics summary called the Standard Model of Particle Physics, include particles that they don't hang around for long. They decay within a short time. And so because they decay, we would not really see them too much, encounter them too much. Using our current understanding, it seems that within 1/1,000,000th of a second of the beginning of time, quarks have sufficient energy to tear themselves free. At earlier times than this, the familiar hadronic particles dissolve into a soup of quarks. Each of the fermions also has a mirror image version called its antiparticle. So you might remember we talked about like two, basically a pair at one point, and that's because all of these particles, all these fermions, actually also have antiparticles. In a sense, never mind. I was going to say something else, but it's not important right now. But anyway, each of the fermions also has an antiparticle. It's sort of a mirror image particle, like a pair partner, basically. And this is an antiparticle. So this is not to be confused with the supersymmetry super partner particle that particles may also have, which is what the concept of supersymmetry theorizes. But this is antiparticle. This is well within the realms of standard model of particle physics. Okay, so for example, electron antiparticle is positron, and that's been seen. It's a thing. It's definitely possible in nature to have a positron. There are more processes that make electrons than do positrons. So we have more electrons generally than positrons. But antiparticles are nothing so bad, nothing too exotic or weird. Just a partner of these particles. Okay. The antiparticle of the electron is a positron. There are also anti-quarks and anti-neutrinos. So sometimes within a particle physics interaction reaction process thing, you might get out the particle or its antiparticle, but the flavor would be one of those flavors that we just talked about. Like it could be an electron, a muon, or a tau, or it could be an anti-electron, an anti-muon, or an anti-tau. Where if it's an anti-electron, we would just call it a positron, or it could be a neutrino that's involved somewhere in some process. But actually, when it does something, it becomes what comes out is an anti-neutrino. For example, you might see sometimes it's denoted with like a bar on top of the symbol. Okay. The theory of QED describes interactions between the charged fermions. Right. So quantum electrodynamics, of course, we're talking about electrodynamics or electromagnetism with quantum mechanics included. So, of course, electromagnetism, it's important between charged particles, right? If there's not a charge, then there is no electromagnetism. There's no electromagnetic force. And so out of all the particles, whoever has charge, whichever ones have charge, are going to interact with the electromagnetic force. So it's going to be like you need to have QED or quantum electrodynamics for these particles that have charge because they have electromagnetism as well as quantum in their life, basically. Okay, so that's one way to kind of think about this. Okay. So the next force to come under the spotlight was the weak nuclear force, which is responsible for the decay of certain radioactive materials. The weak interaction involves all kinds of fermions, including the neutrinos, which, being uncharged, cannot feel the QED interaction. So, by the way, I was mentioning just now that QED is, of course, important when you have charge. Well, guess what? There are particles within the lepton family that don't care about QED because they don't have a charge. They just could not care less. And these are neutrinos. These are the type of particles that I actually worked on in my thesis, or they were involved in my thesis. They were the sort of main character particle in the particle astrophysics that I worked on. But basically, these are what we call very introverted, much, much lighter cousins of the electron, belonging to the same family called leptons, but they don't have a charge, and so they don't interact with electromagnetic force. They don't have that electrodynamics that we might want to talk about otherwise for other particles. So QED, quantum electrodynamics, nothing of that nature needed. For neutrinos, how lovely. They just don't care because they don't have charge, okay? So again, but they do interact with something else. They interact with through another type of force. This is called the weak nuclear force, one of the fundamental four fundamental forces, but they do not care about electromagnetic force, okay? So the weak interaction involves all kinds of fermions, including the neutrinos, which, being uncharged, cannot feel the QED interaction. As in the case of electromagnetism, it's almost like the neutrinos are kind of blind. They don't have charge. It's like they don't see certain things. they don't see certain things, and so and that thing in the case of neutrinos is electromagnetism. How must be lovely, right? Must be lovely. It's almost like they're unbothered. They're unbothered by QED. QED, you can just exist. I don't care because I'm a neutrino. I don't care about QED, is what the neutrino said. Okay. As in the case of electromagnetism, weak forces between particles are mediated by other particles, not photons, but in this case, by massive particles called the W and Z bosons. So once again, electromagnetic force is carried by photons. This is the light particle, as in the particle nature of light is the photon. The quantum nature of light is the photon. It carries the electromagnetic force. When there's two things with charge on them, when there's two particles, such as the electron and proton being a composite of quarks, then there is then there is electromagnetic force between those things, and it's carried by photons. But what about those particles like called neutrinos, who interact through the weak nuclear force, and they do not care. They're unbothered by electromagnetic force. There is something else that carries that weak nuclear force, and these are the W and Z bosons. Again, these were kind of discovered a bit later because the weak nuclear force did not come up right away when all of this was going down. And so what are these? The W and Z bosons are also examples of, first of all, bosons. Somebody was asking about bosons. These two are in the boson category of particle physics. Okay, so again, the particle families are leptons, quarks, and bosons. In the boson family, there's photons, which carry the electromagnetic force. In the case of neutrinos, which are leptons, but they interact through the weak nuclear force. This is carried by the W and Z bosons, which are massive particles. They're not like photons. Photons are actually massless. The fact that these particles have mass, unlike the photon, is the reason why the weak nuclear force has such a short range. And its effects are confined to the tiny scales of an atomic nucleus. Isn't that so crazy that that photons are massless? So it's like their effect can go a larger distance, but W and Z bosons are actually quite massive compared to the photons. And so their effect is very short range. Again, it's a subatomic range kind of effect, right? Weak nuclear force. So anyway, weak nuclear force is mediated by the W and Z bosons. They're massive bosons. The W and Z particles otherwise play the same role in this context as the photon does in QED. They and the photon are examples of what are known as gauge bosons, the theory of the strong interactions responsible for holding the quarks. So now we come to the strong nuclear force. So we've talked about gravitation. We don't understand it in terms of particle physics. Okay, it's a deficiency of particle physics to where we don't really have a theory or an understanding of gravitation with particle physics, but we do have an understanding of gravitation with general relativity. Thank you, Einstein, and thank you, God, right? Coming to the next electromagnetic force, the next fundamental force, which is electromagnetic force, this is mediated through the force particle called photons. Yay, light particles or quantum nature of light will carry that. Then we talked about the weak nuclear force. This is mediated by the force particles called the W and Z bosons. And this force affects, for example, the neutrinos, who only interact actually through this weak nuclear force. They don't care about electromagnetic force, for example. Last is strong nuclear force. Who carries this force and what does it affect? The theory of the strong interactions responsible for holding the quarks together in hadrons. So remember how quarks were always in these composites called hadrons or baryons, depending on if it's the very common and familiar type of quark composite, like protons and neutrons that we all know and love in our atoms that we know and love. Then those are called baryons. And the theory of the strong interactions that keep these quarks together is what is what the strong nuclear force will deal with. So the theory of the strong interactions responsible for holding the quarks together in hadrons or baryons is called quantum chromodynamics, QCD.